It turns out that the continued fraction convergence to a given irrational number not only provide good rational approximations. In fact, they provide optimal rational approximations in the following sense. And we shall write this into the following proposition. And this is about the optimality of rational approximates by continued fractions. The proposition states that U be an irrational number expressed as an infinite continued fraction. And remember, this is a limit of finite continued fractions. So let me remind you that this guy is a limit as n goes to infinity of finite continued fractions. And this, remember, is a limit as n goes to infinity of p sub n over q sub n. And this was given in the equation 3.10, and you can look it up. Now, for any n greater than 1 and pq with q positive but also less than or equal to q sub n, if p over q is not equal to p sub n over q sub n, then we have the following inequality. P sub n minus q sub n times u, the absolute value, is bounded by p minus q times u. And in particular, if you divide both sides of this by q square and use this inequality, you will see immediately that this implies p sub n over q sub n minus u, the absolute value, is less than the absolute value of p over q minus u. So this proposition gives the optimality of rational approximation to an irrational number by continued fractions. In other words, the approximation to an irrational number is the best among all rational approximations given this constraint. So this provides one of the motivations for us to study the continued fractions in number theory. Okay, now let me prove this. First, let me formally write down my argument of this inequality implying this inequality. So the first inequality, let me quickly copy it down here, together with the inequality here, q greater than 0 and less than or equal to q sub n, implies that if you divide both sides of this guy by q squared, noticing this second inequality that q is less than or equal to q sub n. So this left hand side is greater or equal to p sub n minus q sub n u's absolute value divided by q sub n squared. The left hand side is greater or equal to p sub n minus q sub n u's absolute value divided by q sub n times q. First, you want to divide both sides of this inequality by q squared, and you use the second inequality to get the left hand side is greater or equal to this absolute value divided by q times q sub n. And now you multiply this and this both by q. This results in this guy. And the left hand side is just pn divided by qn minus u absolute value, and the right hand side is just p over q minus u absolute value. And this is what we want in here. So this gives the proof of the in particular part. And now it remains to show the first inequality. And the proof of this will be a little bit technical. So now we do this slowly. And first we need to recall some equalities that we derived a while ago. First, we need to use this part of this inequality. And let me copy it here. Recall, we have the inequality u minus pn divided by qn is bounded by 1 over q sub n times q sub n plus 1. This was in the book called the equation 3.13. And if you change n to n plus 1, you get u minus p sub n plus 1 divided by q sub n plus 1 less than 1 over q sub n plus 1 times q sub n plus 2. And now we play a little magic trick. Here's the magic trick. U minus p sub n over q sub n can be broken up into p sub n plus 1 divided by q sub n plus 1 minus p sub n divided by q sub n minus the subtraction p sub n plus 1 divided by q sub n plus 1 minus u. And now at this point, do you remember anything related to this quotient p sub n over q sub n? Let me give you a hint. Remember, we have proved something concerning the inequalities on those quotients. And those quotients are either monotone increasing or decreasing depending on whether n is even or odd, whichever order that is. Now, do you remember that inequality or a system of inequalities? Yeah, I'll let you think about it for a while, and hopefully you will locate it by yourself. The inequality I meant is this one. This one. In the book, this is called the equation 3.11. And let me now copy this guy down here. So here we go. This is equation 3.11. Okay. Now you want to apply 3.11 to this situation. So you will see from this that there are two cases to consider, namely when n is even or when n is odd. So first, if n is even, what happens when n is even? When n is even, this part is positive. This part is also positive because those odd quotients are always greater than the even quotients. So this guy is positive. And likewise, this is also positive. So they are all positive, which can be easily seen from here. So when n is even, the three things in the parentheses are all positive. Now what happens when n is odd? If n is odd, you will see that this part will be negative. And this part will also be negative. And same for this part. So they are all negative. Now you want to combine those two cases. So what you want to do is that you want to combine those cases, and you get, no matter n is even or odd, you will have the absolute value of this first guy is equal to the absolute value of the second guy minus the absolute value of the third guy. Okay, good. And it follows from this equality with absolute values that the right hand side is equal to q sub n times q sub n plus 1. In the numerator you get p sub n plus 1 times q sub n minus p sub n times q sub n plus 1. And you put absolute values. And the second thing, for the second part, we will apply this inequality. This will give us the term above is strictly greater than the term below. So here it is 1 over q sub n plus 1 times q sub n plus 2. Now, can you see how we could simplify this first term? And I tell you, this first term is just 1 over q sub n times q sub n plus 1. And do you see why? This is because of our determinant condition. Remember? At the very beginning, we have this recursive formula, and when you take the determinant of both sides, you get the equation like this, and you take the absolute value, and which gives you 1. This is exactly the same situation in the case we are dealing with. That verifies this. And now, one more step. If you look at this inequality and this inequality here, you combine these two. What you get is absolute value of u minus Pn over Qn is bounded above by 1 over Q sub n plus 1, but below by 1 over Q sub n plus 1 minus 1 over Q sub n plus 1 Q sub n plus 2. And now, you multiply those inequalities by Q sub n. What you get from here is Q sub n times u minus P sub n's absolute value is bounded above by 1 over Q n plus 1, but this is bounded below by 1 over Q plus 1 minus Q sub n over Q sub n plus 1 times Q sub n plus 2. And now I tell you that the left-hand side of this can be further simplified. Indeed, this left-hand side is equal to the fraction with Q sub n plus 1 and Q sub n plus 2 in the denominator, and in the numerator you get Q sub n plus 2 minus Q sub n. But what is Q sub n plus 2 minus Q sub n? This, remember, we derived a recursive formula for Q sub n as well. What I was talking about is this formula. And we copy this down in there. So in this situation, Q sub n plus 2 will be equal to A sub n plus 2 times Q sub n plus 1 plus Q sub n. We're changing n to n plus 1 in here. So this numerator here will be equal to, let me be careful, this should be A sub n plus 1 times Q sub n plus 1. And therefore we can rewrite this. Let me first erase. So in the numerator, what you get in the end will be Q sub n plus 1 times A sub n plus 1. And this is equal to, let me be careful, this should be A sub n plus 2 times Q sub n plus 1. Okay, now let's change this to the thing we want. So now let's first erase this, and we change the numerator to A sub n plus 2 times Q sub n plus 1. And we cancel out this guy from numerator and denominator. And the remaining term will be greater or equal to, recall that this A sub n plus 2 is a positive integer. So the numerator is greater than 1, greater or equal to 1. So this guy will be greater or equal to 1 divided by Q sub n plus 2. Okay, now we have spent a huge effort to get something very simple. That this guy is squeezed between 1 over Q sub n plus 1 and 1 over Q sub n plus 2. Let me copy the results we get in here. What we just got is the absolute value of Pn minus Q sub n times u is bounded below by 1 over Q sub n plus 2, but above by 1 over Q sub n plus 1. This is true for n greater or equal to 1. Because this is so important and we spend so much effort proving it, it deserves a label which is 3.15 as in the book.